Hi guys, today we are going to study about the electrochemistry. In electrochemistry, in this topic or today we are going to study about the introduction of electrochemistry, types of conductors, factors affecting the electrolytic conduction, and the certain basic terminologies used in electrochemistry. In case of an introduction of electrochemistry, electrochemistry is the branch of chemistry which deals with the relationship between the electrical energy and the chemical changes. In case of an electrochemistry, electrical energy is to be used to carry out certain chemical reactions, and certain chemical reactions are converted into the corresponding electrical energy. Both these changes or the relationship between the electrical energy and the chemical energy is studied in electrochemistry. Electrochemistry is nothing but the branch of chemistry which deals with the relationship between electrical energy and the chemical changes takes place in the redox reactions. It is also be nothing but it gives information about the transformation of electrical energy into the chemical energy and the vice versa. When we study the electrochemistry, it is necessary to know what is meant by the conductors, because conductors they play very much role or important role to understand this transformation of electrical energy into the chemical energy and vice versa. Therefore, it is necessary to know what is meant by the conductors. The conductors are the substances which allow the electricity to pass through them. Okay, means the substance which pass the heat and electricity we know that are called as the conductors, and which do not allow the electricity to pass through them, they are called as the insulators. There are the two types of conductors. One is called as the metallic conductor, or it is also be called as the electronic conductors. Second one is electrolytic conductors or ionic conductors. What is meant by the metallic conductors or electronic conductors? We'll see here the differentiating point between these metallic conductors and the electrolytic conductors. In case of a metallic conductors, these metallic conductors conduct electricity without undergoing any decomposition or without undergoing any change into them. And in case of an electrolytic conductors or ionic conductors, they conduct electricity with decomposition, means after passing the electricity through electrolytic conductors, they undergoes a certain chemical changes. That type of conductors are called as the electrolytic conductors. Secondly, in case of a metallic conductors, in case of a metallic conductors, the electricity is flow through them due to the flow of electrons, because we know that metals has a number of free electrons, and therefore that is the flow of electricity is due to the flow of electrons. In case of an electrolytic conductors, they conduct electricity due to the flow of ions. Okay, means when any type of an electrolytic conductors, when we dissolve in a solvent or in aqueous solution, that is the formation of ions takes place or a dissociation of ions takes place, and that is the flow of electricity is due to the flow of ions. In case of metallic conductors, the conduction, electric conduction, it is to be decreases with increase of temperature. Means when the temperature is increased, at that time metallic conduction decreases. Why the metallic conduction it is decreases when the temperature is increased? We know the metals it consists of the metallic bond, and this metallic bond cannot be explained on the basis of traditional bonds like covalent bond, ionic bond, or van der Waals forces of attraction. This metallic bond is explained on the basis of electron C model. What is there in electron C model? Electron C model explains the metallic bond as the metals which is to be positively charged called as the kernels, and these kernels are looks like to be dipped in the sea of electrons. Means there are the number of electrons and small metal ions called kernels are to be dipped in the large number of electrons. And whenever the temperature is increased, at that time these kernels, positively charged metal ions, they vibrates about their mean position. And what happens? When these kernels vibrates, they restrict, they disturb for the flow of electrons from one end to the another end of the metal. And due to that one, the flow of electron is restricted or the speed of electron is decreased, and due to that one, that is the metallic conduction decreases with increase of the temperature. In case of an electrolytic conductors, electrical conduction increases with increasing the temperature. When the temperature is increased, at that time we know that the electrolytic dissociation is increased. Means the number of free ions are to be increased, and the number of ions increase, their speed is also increased with increasing the temperature, and at that time electrolytic conduction is increases, and it is the opposite to the metallic conduction. In case of a metallic conductors, vibrating kernels in the metal offers the resistance during the electronic conductors that we have already discussed. In case of an electrolytic conductors, the resistance is due to the inter-ionic interaction and the viscosity of the solvent. Means there are the certain types of factors which resist the electrolytic conductors, such as inter-ionic interaction, solvation of ions, and the viscosity of the solvent. These three factors decreases with increasing the temperature, and therefore the electrolytic conduction it is increases. Then see here the factors affecting the electrolytic conduction. There are the three factors which affects the electrolytic conduction. First one is the inter-ionic attraction. Second one is solute-solvent interaction. Third one is viscosity. Let us see one by one. Firstly, we will see about the inter-ionic attraction, which depends upon the solute, that is, and solute attraction, and therefore it is also be called as solute-solute interaction. Means if there is a more solute-solute interaction, then at that time there is a less number of ions are dissociated in aqueous solution. As the less number of ions are dissociated in aqueous solution, there are the less number of ions, the speed of the ion is decreases, and due to that one, that is the electrolytic conduction, it is decreases. The second one is solute-solvent interaction. Means there is a more attraction is there between the solute and the solvent molecules. It is also be called as the solvation of ions. If the solvation of ions is more, then at that time electrolytic conduction is decreases. Means the ions are to be surrounded by the what? The solvent molecules, and therefore the solvent molecules, they restrict for the flow of ions. It decreases the speed of ions, and therefore if there is a solute solvent interaction is there is the more attraction between the solute and solvent. Now at that time it restricts the electrolytic conduction, and therefore the electrolytic conduction is decreases with the solute solvent interaction increases. Similarly, third one is the viscosity. The viscosity is also nothing but the solvent solvent interaction. Means it depends upon the solvent solvent interaction. If there is a more attraction between the molecules of the solvent, then at that time that solvent becomes a more viscous, and therefore that resist for the flow of ions in the solvent. They resist the speed of the ions in the solvent, and therefore the electrolytic conduction is decreases. When we increase the temperature, all these factors such as intraionic attraction, solvation of ions, viscosity of the solvent decreases with increasing the temperature, and due to that one the electrolytic conduction increases. The effect of all these factors decreases with increasing the temperature, and hence the electrolytic conduction increases with increasing of temperature. On the other hand, the electrical conduction of the electronic conductors decreases with increase of temperature. Okay, guys, these are the certain types of factors which affect the electrolytic conduction. Means as all these factors decreases with increasing the temperature, and therefore obviously electrolytic conduction increases. There are the certain types of terminologies used in electrochemistry. The first terminology which we are going to study is the resistance. See here, every substance offers hindrance to the flow of electricity to a smaller or the large extent, and this hindrance to the flow of electricity is called as the resistance. And we know that the exact value of this resistance is offered, or it is to be determined from the law. That law is known as the Ohm's law. What is the Ohm's law? If to the ends of the conductor a voltage is applied and the current I flows through it, then the resistance, that is to be denoted with the R, of the conductor is nothing but the voltage upon the current flow through the conductor. Okay, means here in this case that current is generally measured in amperes, whereas the voltage is measured in volt. If 1 ampere current is flow through a conductor, 1 voltage of 1 volt is applied to it, the resistance of the conductor is taken as 1 ohm. See here, This is the conductor, and when we apply the voltage across the two ends of this conductor, and if I is the current flow through them, then resistance is nothing but the voltage divided by the what? A current. Means the resistance is to be inversely proportional. Suppose it is directly proportional. Sorry, this is the L is nothing but the suppose a length of the conductor, and A is the area of cross section. Means here in this case, resistance is directly proportional to the length of the conductor, and it is inversely proportional to its area of cross section. Therefore, we call R is proportional to the L upon A, and therefore, if you have taken rho is the what resistivity, that is called as the specific resistance, that is to be the constant, then at that time R is to be equal to rho is equal to L upon A. The unit of the resistance is ohm, and the rho is nothing but the resistivity, or it is the specific resistance, and its unit is nothing but the what? Rho. Then in detail about the resistivity and the specific resistance we'll see in the next slide. Then see here conductance. What is the conductance? It is reciprocal of resistance is called as the conductance. Here in this case, it is common practice to speak of the conductance of the solution rather than its resistance. Okay, the conductors allow the electricity to pass through them, and in this case, the unit of conductors, it is the reciprocal of ohm, or it is to be written as mho, or it is to be denoted with the mho, or the unit of resistance is the Siemens, that is to be denoted with the what? S. Means in this case, the conductance of any conductor or the flow of electricity in any conductor, it is to be measured in conductance rather than its resistance. Means conductance is the one of the common practice to show the conductance of the solution, okay, rather than the resistance. Then see here what is meant by the specific conductance. It is observed that resistance R of a conductor is directly proportional to the length, we know, and it is inversely proportional to the area of cross section. See here what we have studied here. That is, the resistance is to be directly proportional to the length, and it is inversely proportional to its area of cross section. Okay, that is here in this case the reciprocal of the specific resistance of an electrolyte, that is called as the specific resistance. Specific conductance, it is nothing but the reciprocal of specific resistance of an electrolyte. Specific conductance, it is to be denoted with the letter, that is the K, that is what we call a kappa. That is the specific resistance, kappa, it is nothing but the what? 1 upon rho. But we know rho is nothing but the A upon L into R, which is to be modified with the equation of resistance, that is R is equal to rho into L upon A, and it is to be modified as rho is equal to A upon L into R. That is the specific conductance. It is the L upon A into R, where L is the length of the conductor, A is the area of cross section of the conductor, and 1 upon R is nothing but the conductance, and therefore what we call that is the K is equal to L upon A into the conductance. And we know that L upon A is known as the cell constant. Okay, L and A of any cell, it is to be the constant, and therefore it is nothing called as the cell constant. Okay, cell constant for a given cell with fixed electrode is a constant, and it is called as the cell constant, means length and area of cross section for a particular electrode, it is to be the same, or it is fixed for the electrode, and it is called as the cell constant. The unit of specific conductance is per ohm per centimeter. Okay, see here in this case, that is the SI unit of specific conductance is Siemens per centimeter, because per ohm it is nothing but the Siemens. It is maybe written in case of an per meter, where S it is nothing but the Siemens. We know already it is the unit of the conductance. Okay, then here in this case this is about the specific conductance. Next is nothing but there is specific resistance. Then what is meant by the specific resistance here? See here, the resistance of the conductor that we already saw, it is to be directly proportional to the length, and it is inversely proportional to the area of cross section. Therefore R is directly proportional to L upon A. R is equal to rho L upon A. That is, rho is the proportionality constant called the specific resistance or resistivity. The reciprocal of resistivity is known as the specific conductance, or simply it is the conductivity called as the kappa. If K is the specific conductance and C is the conductance of the solution, then we know the resistance is the reciprocal of conductance, that is R is equal to 1 upon C, where L is the 1 centimeter and area is the 1 centimeter square. Then rho is equal to 1 upon K, that is the specific conductance. Okay, means specific resistance is the reciprocal of specific conductance. Then we know that is R is nothing but the 1 upon C, that is equal to 1 upon K into 1 upon A, and therefore that is whatever may be the specific conductance kappa is equal to C into L upon A, and where L is 1 centimeter and the area of cross section for a particular conductor is the A, that is 1 centimeter square. At that time, that is the K is equal to C, means for a particular conductor when the length is 1 centimeter and its area of cross section is an 1 centimeter square, that we call for particular conductor L upon A is constant. L upon A is constant, that is called as the cell constant, and this is the constant, means when L is 1 centimeter and A is then 1 centimeter square, then at that time what happens? At that time the specific conductance is equal to the conductance. Okay, that we have understand. Then see here, what is meant by the specific conductance in detail. The specific conductance of a solution is the conductance of a solution of 1 centimeter length and having 1 centimeter square area of cross section. Mean the conductance of a solution which has the 1 centimeter length and having 1 centimeter square area of cross section, that conductance of the solution will be the specific conductance. Simply what we call the conductance of 1 centimeter cube of the solution of the electrolyte is called as the specific conductance. Suppose here in this case, this is the cube and this cube has the 1 centimeter length and its area of cross section is the 1 centimeter square. Here in this case, if we dissolve a particular solute in an electrolyte having its volume 1 centimeter cube, then at that time the conductance of that solution becomes an specific conductance. And the conductance of this cube, it is nothing but the specific conductance. This is about a specific conductance. Means if we dissolve any solute in a solvent having the 1 centimeter cube volume and we taken that solvent in this 1 centimeter cube vessel, then at that time the whatever may be the conductance of that electrolytic solution, it is nothing but the for specific conductance. Simply what we call that is conductance of 1 centimeter cube of the solution of the electrolyte is called as the specific conductance. Then now we will see about the equivalent conductance. What is the equivalent conductance? Equivalent conductance of a solution at a dilution is defined as the conductance of all the ions produced from 1 gram equivalent of electrolyte dissolved in V centimeter cube of the solution, and it is denoted by the lambda equivalent. See what is meant by the equivalent conductance. Okay, means if we have taken the V centimeter cube of this solvent and we dissolve a 1 gram equivalent of electrolyte, that is 1 gram electrolyte, it produces all the ions, and whatever may be the conductance of that electrolytic solution, it is called as its equivalent conductance. And this equivalent conductance, it is nothing but, or it is the volume into the specific conductance. Means here in this case, that is a specific conductance and equivalent conductance, they are related to each other through the volume of the electrolytic solution. Lambda equivalent is nothing but the volume into specific conductance, and this lambda equivalent is equal to specific conductance into 1000 divided by n. Then how it is, we will see here. See here, this is a one type of an vessel which has these two walls, and these two walls of the vessel are to be considered as the electrodes. One is cathode, another one is anode. To understand this relationship between a specific conductance and the electrolytic conductor, equivalent conductor, we know the equivalent conductance of the solution is usually not found directly, but it is calculated from the specific conductance. The relation between the equivalent conductance and specific conductance can be obtained by considering a rectangular vessel, this rectangular vessel with its two opposite walls 1 centimeter apart and made up of some metals, so that these acts as an electrodes. The relationship between the equivalent conductance and specific conductance is understand. Suppose a 1 centimeter cube of the solution contains 1 gram equivalent of the electrolyte. The conductance of the solution will be then its specific conductance. Further, if 1 centimeter cube of the solution taken contains 1 gram equivalent of the electrolyte, the conductance of the solution will be equivalent conductance. By the definition, we know. Thus, means when 1 centimeter cube of the solution contains 1 gram of equivalent of an electrolyte is considered, then at that time the specific conductance and equivalent conductance are same. Means here in this case volume is 1 centimeter cube and the 1 gram equivalent of the substance or electrolyte is dissolved, then at that time total volume of the electrolytic solution is 1 centimeter cube and its conductance becomes a specific conductance. And according to the definition of equivalent conductance, conductance is that solution which contains 1 gram equivalent weight of the solute or electrolyte. And therefore, whatever may be the conductance is an equivalent conductance, it is also the specific conductance. Means the value of equivalent conductance and specific conductance is same. If we have taken the electrolytic solution having the V centimeter cube of the volume, suppose here in this vessel we have taken a 9 centimeter cube of the volume of the electrolytic solution, and if we pass the electricity, then at that time what happens? Conductance of the solution is equivalent conductance, not an specific conductance, because the volume of the solution, electrolytic solution, is 9 centimeter cube, not an 1 centimeter cube. If we have considered the conductance of this 1 cube which having the length 1 centimeter and its area of cross section is 1 centimeter cube, and therefore the volume of this cube is 1 centimeter cube, and if we consider the conductance of this 1 cube, it is nothing but the specific conductance. And if we have considered the conductance of this whole vessel, it is nothing but the what? Equivalent conductance. Because equivalent conductance, it depends upon the amount of the solute dissolved in a solvent, means that amount is equal to gram equivalent weight of that solvent. A specific conductance, it depends upon the volume of the solvent. Volume of the solvent required for a specific conductance is 1 centimeter cube. It does not depend upon how much solute it is to be dissolved, but equivalent conductance, it depends upon the how much solute, that is the gram equivalent of the solute, it is dissolved in a V centimeter cube of the solvent. And therefore what we call that is the equivalent conductance is equal to the specific conductance into the what? Volume. Okay, means here in this case equivalent conductance of this vessel, it is nothing but the specific conductance, or it is here in this case of 1 cube is nothing but the specific conductance, and conductance of this whole vessel, it is nothing but the equivalent conductance, and this equivalent conductance, it is equal to conductance of the 9 cube into the what? A specific conductance. Okay, means what is this 9? 9 is nothing but the what? Volume of this electrolytic solution placed in the vessel, and therefore what we determine the equivalent conductance is equal to the specific conductance into the V, and therefore V is nothing but the what? Volume of the electrolytic solution, and therefore the lambda equivalent is equal to K into V, where it is the kappa, that is specific conductance into the volume of the electrolytic solution. Okay, if C gram of this electrolyte, it dissolved in 1000 centimeter cube of the solvent, means 1 liter of the solvent, then volume of the solution containing 1 gram equivalent is equal to the what? 1000 centimeter cube. Hence, this equation 1, it is to be written as, that is the lambda equivalent into the specific conductance at particular concentration C into, that is 1000 divided by C equivalent, and that is nothing but the specific conductance at concentration C into 1000, and C equivalent, it is nothing but the normality, because a C gram equivalent of the substance it dissolved in 1 liter, that is nothing but the what? A normality, means gram equivalent of the substance dissolved in 1 liter of the solvent, it is nothing but the normality. Here in this case we dissolved C gram, means that is to be measured as an what? Normality. Okay, this is the relationship between the equivalent conductance and the specific conductance. What is the relationship? That is the lambda equivalent, it is nothing but the specific conductance into 1000 divided by normality. Now what is the unit of the equivalent conductance? We know equivalent conductance is equal to specific conductance into the volume, that is equal to, that is the unit of specific conductance is per ohm per centimeter, and volume is in 1000 centimeter cube, means it is the centimeter cube divided by, that is the gram equivalent. V is nothing but the what? 1000 divided by normality, and therefore 1000 it is then centimeter cube, that is a volume of the solvent, and the amount of the solute is gram equivalent, and therefore the unit becomes, that is the per ohm per centimeter per gram equivalent, or it is nothing but, that is the Siemens centimeter square per equivalent, or it is nothing but, that is the per ohm centimeter square per equivalent. Okay, this is about the what we call, that is the per centimeter or per centimeter per equivalent. This is the unit of what we call, that is the equivalent conductance. The next one is the molar conductance. It is the similar to the equivalent conductance. At the molar conductance of a solution at a dilution V is the conductance of all the ions produced from 1 mole of the electrolyte dissolved in V centimeter cube of the solution when the electrodes are 1 centimeter apart and the area of the electrode is so large that the whole solution is contained between them. Means here in this case molar conductance of the solution containing 1 mole of the electrolyte in V centimeter cube of the solution, means when 1 mole of the solute is dissolved in V centimeter cube of the solvent, then at that time the conductance of that solution becomes a molar conductance. Okay, and this molar conductance, it is to be shown with the lambda m, or it is to be shown with the mu, and it is also be related with the specific conductance with the volume, as molar conductance is equal to the specific conductance into the what? A volume V centimeter cube of the volume solvent. Okay, and therefore it is also be nothing but similar to the equivalent conductance, that is the specific molar conductance is equal to kappa, that is the specific conductance into this 1000 divided by its molecular weight, gram mole of the substance dissolved in 1000 centimeter cube of the solvent. Okay, where V is the volume in centimeter cube, mu or lambda m is nothing but the molar conductance, K is nothing but the specific conductance, and m is the molarity of the solution. Okay, and therefore the SI unit of the molar conductance is per ohm centimeter square per mole, or Siemens meter square, that is a per mole. Then similarly the relationship between the molar conductance and the specific conductance, it is to be denoted, or it is to be shown as molar conductance is equal to the specific conductance into the volume, or that is the molar conductance is equal to the specific conductance, that is 1000 divided by C. C is nothing but the what? That is the C gram of the solute dissolving 1000 centimeter cube of the solution, that is nothing but the for a molarity, and therefore K is equal to, so that is nothing but at the lambda m means molar conductance is equal to specific conductance into 1000 divided by molarity. Okay, this is the relationship between the molar conductance and the specific conductance. Guys, here in this case, we have studied the terminologies, introduction about the electrochemistry, that is the terminologies used in case of an electrochemistry. If we understand all the concepts, if we understand all the terminologies used in electrolytic electrochemistry, please like, subscribe this video for getting the more information about the electrochemistry. Thank you.